Okay, nice. Recording in progress. So, hello everyone. Today we start lecture number 7. This lecture will be about monoidal and enriched categories. There is a lot of material in it. I'm not sure that we will finish everything today, but we will start, and I think we'll do the main part precisely today. So, what we are going to talk today about? We are going to talk about categories where morphisms between any two objects form not just merely a set, but an object of a certain category, which is not necessarily set-like. So to start with, we cannot start immediately from a definition of enriched category because we need our objects, new home objects, not home sets, but home objects to live in some setting, which will be convenient for all our notions of category, functor, natural transformation, and so on. The reason is that we are using often mindlessly operations in a category of sets and even not noticing how perfect category set is for all needs that we have, but not for exactly all needs, especially when we have some additional structure that we want to keep on our home sets. Therefore, I decided to start with a definition of a so-called monoidal category. And to jump in this definition, I want to look first at two observations, one for category of sets, one for category of abelian groups, that we all know, but they can give us a hint why we do precisely this way, not the other one. So first of all, let's observe that in a category of sets, the choice of an element f from a set X is a map from a one-point set. I'm right now highlighting where I am reading. I prepared a little, very little. It's a map from one-point set to our given set X, which picks up element F. I also call this map F. That's the first observation about the choice of element. The second observation is that Cartesian product X cross Y gives us all pairs of X and Y, where X belongs to X and Y belongs to Y. So Cartesian product is a set of all pairs. And moreover, we have relations between our one-point set and product. What are these relations? That Cartesian product with one-point set is isomorphic to set itself. Doesn't matter on which side we are taking product. So these are very beautiful properties that we have: choice of element, product, and relation between singleton and a product. As you see, that singleton plays a very distinguished role in this case. Another construction is for abelian groups. I decided to copy all the text above, and I changed the things that I want to be changed with a blue color. So for abelian groups, the choice of element F from an abelian group A is a map from Z to A, and moreover, this map is group homomorphism. So I need to write down, it's not just a function, it's a group homomorphism from Z to A. Every group homomorphism from Z to A is uniquely determined by its value on identity element. So this value on this identity element is precisely element F that we are picking up from our abelian group A. Instead of product X cross Y, in the case of abelian groups, we need to look at tensor product of abelian groups A and B. This gives us not all pairs A cross B, where A belongs to A and B belongs to B, but some pairs, because we have conditions of additivity and linearity on every component. Also, elements of abelian group A cross B are not pure tensors, so A tensor B, but sums of such tensors A, B. And we have similar relations to relations in set between Z and tensor product. The tensor product of any abelian group with Z on either side is isomorphic to group itself, to abelian group A itself. So we see that there are differences for category of sets and category of abelian groups. And these differences we want to encode in the in some definitions that will carry both pluses and minuses of both constructions. This is so-called definition of monoidal category. But to do it, I want to proceed in a couple of steps. Many of you have seen the definition of monoidal category in different forms. I will give you an inductive definition. So step by step, I will be enriching the structure that exists on a category. And finally, we will arrive to a monoidal one. So first of all, consider category V. It's just a category. And together with it, consider a functor, which is a bifunctor. I denote it by tensor product symbol, which acts from V cross V to category V. It's just bifunctor. Together, they form this pair category with tensor product. And we will denote this pair V, comma, tensor. And this operation will be called, of course, tensor product. So this is our tensor product on a category. Second definition is the following: that a set of isomorphisms as in a category with tensor product V, comma, tensor is said to be coherent. The main word here is coherent if any isomorphism manufactured from elements of S, their inverses and identities comma under the, I will say not comma, I can parenthesis, under the tensor product is the identity morphism. What does it mean under the tensor product? That we will combine tensor product operation together with isomorphisms from S, excuse me, their inverses and identity. So together making all possible morphism from a single object will be identity morphism. For instance, take here one object. Here we'll take S1. Here we'll take certain S2. Here we'll take S3 inverse. Here we will take S4 cross 1. tensor 1. Here we'll take S5 minus first. And here will be for third S6. If this, if we have such diagram, and all this S's belongs to S, then from this we will follow that composition. This composition is an identity. So the automorphism manufactures from elements of S, their inverses, identities, and tensor product is an identity. Such set of isomorphisms will be called coherent. It's a very general definition. And to see it in action, we need to define a couple more natural isomorphisms that are related to tensor product operation, and then we will see how it gives us the definition of monoidal category. So part 3 of the definition, so let V, comma, tensor product be a category with tensor product. A natural isomorphism which we call alpha sub A, B, C, which goes from A tensor B tensor C to A tensor B tensor C is called an associative. So we defined a tensor product as a bifunctor. This bifunctor we want to be similar to product operation or tensor product operation for abelian groups. As we know, such operations usually are associative. And this associativity is given by certain isomorphisms. Since it needs to be factorial, we could get a natural isomorphism. This natural isomorphism will be denoted as alpha, and it will have subscript of all three letters that appear, A, B, and C. Okay, and I also want to draw a diagram just for practice. So how we can unravel such definition of certain natural isomorphism and see the picture of functors and natural transformations under it. So here we have three letters, A, B, and C. Therefore, we need to start from a single vertex where we have a category V 3 times. Then we are taking products in 2 different ways. In the first way, we are taking product of second and third component, tensor product, and first is preserved the same. So I'm taking the identity functor cross tensor product. So identity will keep the first component and tensor product will multiply second and third. We will then get to V cross V. There is another way, which is on the right hand side. First, multiply first and second component, and the third keep. And afterwards, in both left and right side, both results need to be multiplied together. And we are getting the result at V. So here will be tensor product operation, here will be tensor product operation. The upper and right arrow correspond to a left-hand side and other arrows to a right-hand side. So here we have a 2 cell filled with a natural isomorphism alpha, which is called associative. That's how this axiom looks. Okay, part B. Other isomorphisms that we will need are the following. So if there exists an object I belonging to V such that there are natural isomorphism E times A to A called lambda sub A, and A cross, not E, excuse me, I to A called rho sub A, we say that I is a unit of our tensor product and lambda sub A, rho sub A are called left and right uniters respectively. So in this definition we have a unit object, unit of our operation, and left and right uniters. Sometimes this object is called also identity object. I can sometimes call it also identity object, so be ready for that. Okay, how we should look at these axioms. At these axioms we should look again as of diagrams. Of course, we naturally can understand this as something that reminds us as a formula that I just circled, multiplication by z, tensor product with z on either side, and these natural isomorphisms. But to understand a little more how we work with it, we need to draw diagram. So in the center of the diagram, excuse me, I'm constantly calling it V, will be a pair. In this pair, one of the elements is identity or unit I, and another is as an arbitrary object A. So as we know, to pick up an element or an object from a category, it is enough to define a function from a trivial category. We did it already many times. Another category we are taking to BV. So first we are taking identity, and then we are taking any element. So using this functor, we are getting pair. First element in this pair, it's I, and second is arbitrary object A. Then we multiply them using tensor product operation, and we are getting to V. Also, we have a natural isomorphism that taking product of a trivial category with any category is also any category. This two cell that fills this triangle is a lambda, our natural isomorphism lambda. Also, we have a symmetric right part where we are picking up identity in the second component. Also, we have isomorphism here, and we have natural isomorphism rho filling this two cell. Okay, and part C. It will be about a so-called braiding. In certain categories, it is present. In certain categories, it's absent. But in all the examples that we will be looking at, it will occur. So a natural isomorphism, let's call it beta AB, from A tensor B to B tensor A is called a braiding on V. So keyword here is braiding. How we can draw a diagram for it? So we will take a pair from category V. Then we will twist this pair with tau. It's just interchange of components. And from the other side, we will take tensor product of components of the pair. And here is beta, the two cells filling this diagram. The upper functor, of course, is an isomorphism. So tau minus first is tau, so it doesn't matter which component we will where beta will go. Also, beta is an isomorphism. Okay, to finish, I will use the corner which is still left on our board and say that associator reminds us associativity of product. Uniters, it is multiplication with identity. And braiding is commutativity. Commutativity of our operation. And tensor product operation on a category is a way how we can multiply objects between themselves. Okay, so I'm finishing this screen, and if there are no objections, I will move to the next screen. So I will put everything up. Anytime I can move my screen in either way, so you can recover. Is it okay, or I should wait a little? Also, you can always take screenshots at any point, and everything is recorded. So can I move forward? I see two people noting, three, Rahul and Alon. Can I?
Sounds good to me.
Thank you so much. I see your thumbs up. Okay. Yeah, and it does. The system does not allow me to put everything down so easily. So I have a tail. Okay, let this tail be preserved. I will again go in couple columns. It helps me to make more structured text. So we talked about these properties, and now I want to gather them all in one definition. So I will use definition number 4, and we say that a triple category V, tensor product and unit object I is a, in parentheses, braided monoidal category if two conditions are satisfied. First, V and tensor is a category tensor product. Second condition. There are associator alpha, left and right unitors lambda and rho, and in parentheses braiding beta, and I is a unit. Is a unit of tensor product, but it's not enough. And third condition, that set of all associators unitors. I'm abusing the notation, of course, not associators, but their components. But still, I will call components associators. Unitors, in parentheses, braidings, together with their inverses and identities and tensor product operation is a coherent set. So let's draw anything. I'm just imagining A, tensor B, tensor I, tensor C. In this way, I'm putting parentheses, goes to A, tensor I, tensor B, tensor C. No, I can directly do that. 1 second. A, tensor B, tensor I, tensor C will go here as A, tensor B, tensor C. Here it will go as A cross B, tensor I, tensor C. Will go to A, tensor B, tensor I, tensor C. Then it will go to A, tensor B, tensor C. And then it will go this way. Okay, so here what I have here, I have associator using associativity. Here I have used rho minus first. Oh no, not minus first, just rho. On other arrow, on the other side, I again have used associator. Then later, inside parentheses, I used associator cross identity on C. Then, yeah, here it's not just rho, it's identity, then cross. Wait, not cross. So it's identity tensor, identity tensor rho. Oh, this is more precisely. Here it will be identity tensor rho again. Tensor identity, and the last is just alpha. So this diagram necessarily commutes. So it doesn't matter how I perform the operation. You can do all the operations as you used to perform. with associativity, commutativity, multiplying by identities in every single way. Doesn't matter which diagram you draw. This diagram will be commutative. That's what says coherent. So we can perform our operations in any order and still get the same result. If in this diagram we will add for a second some other isomorphism from outside this set of associators, uniters, braidings, and so on, then we won't necessarily obtain the same isomorphism. But still, if we enclose ourselves only to such set, then everything will work out and we will get commutative diagram. This thing can be simplified as not every, we don't need to describe every diagram. We just need to have certain axioms for certain types of diagrams, and this is enough for us. But I won't go in the details. It's more about how to define a monoidal category. This is one of the ways how to define it, one of the equivalent ways, and in my opinion, it hits all the necessary points. That we have coherence of all our distinguished maps in a monoidal category. Additionally, if beta minus first equals beta, we say that V tensor identity is a symmetric monoidal category. So in symmetric monoidal category, braiding, applying braiding twice will return us the original object. Well, and number, the last property that we need to look at is a case when we can not only multiply objects, but also, let's say, divide them. That's not precisely, but in certain way to divide them. So if for any object A belonging to V, a functor blank tensor A going from V to V has right adjoint we say that V tensor I is closed. So this bifunctor will be denoted with square brackets. First component of it, it's contravariant. Second component is covariant, and the result is again in V. This bifunctor will be called internal home of category V. So we can write, let's X tensor A comma Y in a category V is isomorphic to, isomorphic as a set, by the way, V X internal home from A to Y. So this is in set. So now let's look at a couple of properties. Here we assume that V tensor identity and internal home is a closed symmetric monoidal category. So properties, first property, that we can substitute in the isomorphism above home in category V by internal home. So internal home acts really as a home. Second property, internal home from I to X is isomorphic to X. Third property, X times Y Z isomorphic to X internal home YZ isomorphic to Y comma internal home from X to Z. In other words, blank comma Z from V of to V is a contravariant functor, comma, and which is right contravariantly adjoint. As we had this notation before, so I'm drawing arrow in the direction where it is adjoint. So we have such a junction, which is given by formula 3 precisely. So when we fix covariant component in the internal home, then it has left adjoint, which is a tensor product. If we fix covariant component and contravariant varies, then it's self-adjoint. There are many more properties, which are pretty much arithmetical ones, but I don't have much time to go in them. I would say that's enough for monoidal categories. Are there any questions? Okay, if there are no questions, then I will again move my board. And now let's start talking about enriched categories. So monoidal categories give us the common framework for different types of categories that we use in real life. We pack in one definition all the operations that we need to do categorically theoretical constructions. Right now, we will define a category where objects are, excuse me, not objects, home sets are objects of a certain other category. So right now, we're going to jump directly in enriched categories. So let V tensor I be a monoidal category. Right now, as you see, I don't even need braid, symmetric, or closed, so on. It's even enough this. However, every time you can assume that it has all these properties. Moreover, for simplicity, if everything what I'm talking about today is difficult, imagine instead of V, abelian groups or sets. If you imagine category of sets, everything boils down to the regular definition of a category, or so-called ordinary category. If you have V equal abelian groups, it will give you a pre-additive category. So category where Hom sets are abelian groups. We can add and subtract homomorphism from each other. But still we can give a much more general definition. So if we have V as a monoidal category, then a V category A underline. So all enriched categories will be denoted by a script capital letters with underline, or a category enriched in V. So we call it A underline as a category enriched in V, or just V category. Consists of, and we have now data. First, a class of objects of A, P, for every X, Y pair of elements in ob A, for every pair of elements in a class of objects, A from X to Y, which is also denoted as A XY using Einstein notation. This is an element of V, which is called object of morphisms. You also can call it Hom object. C, for every X belonging to objects of A, there is an arrow from identity, from a unit, excuse me, object of monoidal category to our object of morphism from A, X to X. Well, how we will call it? Let's call it, of course you can call it 1 sub X, whatever. Just let's call it for right now, or ID sub X, which is called identity element. D, for every X, Y, Z in objects, there exists a composition morphism. So A from Y to Z tensor A from X to Y going to A from X to Z, which we called CXYZ. It is a composition morphism. This morphism lives in category V. as homes are not sets anymore, but homes are objects. Therefore, tensor product between two home objects reminds us Cartesian products of sets, and function that was taken to morphism and given their composition is not a function anymore between sets, is a morphism in V, which called composition morphism, such that this data satisfies two axioms. First axiom is associativity. And the second axiom is unitality. Let's draw the first one. So A, Z to W, tensor A, Y to Z, tensor A from X to Y, going to A, Z, W, tensor A. We are composing last two from X to Z. Here is another way. A, Y, W, cross A, X, Y. And here is A, X, W. Here is one tensor composition X, Y, Z. Here is composition Y, Z, W, tensor 1. Here is a composition X, Z, W. Here is a composition C, X, Y. Excuse me, here should be W. Yes. So this diagram commutes. And second, unitality. So A from X to Y, tensor identity, go into A from X to Y, cross A from X to X, going under composition to A, X, Y. Here is rho, right uniter. Here is identity, cross ID sub X. And here is CXXY. This triangle commutes. And also here is similar triangle. I don't want to write it down. You can write it yourself. For left uniter. So you have, as expected, multiplication, composition on the left and composition of on the right of your morphism is the same morphism. And above is associativity. This was first and last time when I was drawing all this composition sub something. Usually these subscripts are oppressed. What is not oppressed are home sets. So home, as you see, home sets are appearing in big quantities. They are the main objects. Excuse me, I'm constantly saying home sets. Home objects. So home object has three components. First is a category where it lives, and then are actual arguments. So object from where we start and object where we land. Okay. And since they appear in big quantities, it's much more convenient to use Einstein notation, meaning that the domain of morphism is a superscript and codomain of every morphism is a subscript. This allows us to draw more compact diagrams. So this was a definition of an enriched category. Right now, I want to give you a list of basic examples that we will be using throughout the course of our monoidal categories. Excuse me, not yes, monoidal categories and enrichment. So examples of monoidal categories. So first, if we will take sets with Cartesian product and a singleton as a unit element, this gives us ordinary categories. Again, if you are not very comfortable with all the enriched stuff, you can always imagine that you are working with ordinary category. And I am writing in a very fancy way, well-known notion. Second is category of abelian groups, tensor product, and integers. This gives us pre-additive category. These are categories from which you start learning homological algebra and related topics. Of course, you will then go from pre-additive category to additive one, where you have direct sum of objects, then to abelian one, where you have kernels, co-kernels, but all they are pre-additive categories. So the categories where home objects are abelian groups. Well, third one is a category of small categories, Cartesian product of small categories and trivial category 0. This gives us two categories. Four. Compactly generated weakly Hausdorff topological spaces together with product and 1-point set. This gives us topological categories. So here I will write that these are, I don't want to go inside the definition, it's very long. So it's compactly generated weakly Hausdorff topological space. You can take locally compact spaces, they are compactly generated weakly Hausdorff and substitute it with that, or some more narrow class and so on. But these are just enough. These are topological spaces that are usually enough to work with. They take all other examples. As you see, I do not use all topological spaces. The reason will be clear very soon. So for monoidal categories, you of course can take topological, all topological spaces, but for other reasons why I want to work only in, not over all topological spaces, but under certain topological spaces, as I mentioned, will be clear very soon. Okay, now I will get simplicial sets, products of simplicial sets, and well, also trivial simplicial set consisting of one object. These are simplicially enriched categories. Sixth, this is a generalization of 2. If R is a commutative ring, we take R modules, tensor product over R, and ring R. Seven, you can take chain complexes in R modules, tensor products of chain complexes, and chain complex 0, R, zeros, this chain complex where it's it is R is sitting in degree 0. And then you will work with DG categories. DG category is a little more fancy thing, but still they are enriched in chain complexes. 8, this will be a little surprising example. The category that consists of 2 objects, 0, 1. We are taking monoidal operation as minimum and unit 0 object. I don't remember how these categories are called, but this thing describes for us a relation. So either a relation between 2 categories or not. So 1 if there is a relation, 0 if not. All the examples, my last note on this page, all these examples are closed symmetric monoidal categories that are bicomplete. Such categories are called cosmoi in a single cosmos. So cosmos is a perfect category to do enriched category theory. Closed symmetric monoidal category that is bicomplete. They are the main objects that we will be using during our lectures. So every time you think about enriched category, it's okay to think that you are working over cosmos. Of course, not every definition uses all the properties of cosmos. Closeness or symmetry or completeness or co-completeness. Still, you always think about your certain favorite type of categories you work with, and it's either Billion groups or sets or topological spaces or whatever. And you, this or other way, are thinking about a certain cosmos. So everything is okay. Cosmos keeps things perfect. It's a paradise for doing enriched category theory. From now on, I will be not always describing you what type of category I'm working with. You can always think that I'm assuming this to be cosmos. If not, no, this won't be a case. So always it will be enough. Good. Are there any questions? Because you haven't asked me any question today, no one. So please tell me something. I'm afraid that everything is either so clear that I am wasting your time, or everything is so unclear that I'm talking to myself. Rahul, you switched the camera on. Maybe you have a question from room 575 Lake Hall.
No.
Okay. Well, since we gave a couple examples of monoidal categories, now enriched categories, as you saw, the basis of enrichment generates well-known notions. I want to give a couple constructions. This couple of constructions are very well known for ordinary categories that we even not always think about them, but still we need to work with them axiomatically in the case of enriched category. So first one is opposite category. It's opposite category. Opposite category A op. So who are objects of A op? Now you know we need to specify 4 types of data. A, objects, then B, morphisms, C, identities, and D, composition. So who are the objects? Objects are the same as in A. Morphisms. A op from X to Y is defined to be A from Y to X. That's straightforward. Identities. Identities. The same as in A, comma, using identification and which what is identification? A op from X to X, we identify with A from X to X. Now composition. Well, with composition, it's a little not tricky, but I would say hairy. So A op from Y to Z cross A op from X to Y should go to A op from X to Z. What should we do? Let's write down what is the left-hand side. So it's A from Y, from Z to Y, the tensor A from Y to X. Using braiding, beta, this is isomorphic to the product where we switch the order. And then using the composition, again, I violate my own convention, so I wrote composition component-wise, so Z, Y, X, and we get object from Z to X. But this is precisely the object of morphism in an opposite category from X to Z. So composition in opposite category is twisted by braiding. That's it. Second, is tensor product of categories. Let's say now V categories. So every time I will be talking about enriched categories, I can just say V categories, meaning that they're enriched somewhat. So how it works? A and B are V categories. We define then objects of A tensor B. Can you hear me well? Because I get a notification that my computer is quite busy and you can hear me better. So if you experience certain sound difficulties, please let me know. So objects in product of categories, it's product of classes of objects. Okay, thank you. Thank you so much. B. What about morphisms? Well, with morphisms, this will go in the following way. So A tensor B from pair AB to pair A prime B prime will be defined as A from A to A prime tensor B from B to B prime. C, identities. We have that identity, a unit object is isomorphic to unit tensor unit itself by either left, either right braiding, sorry, not braiding, unit or whatever. Then we are picking up identity in A, tensor identity B, where in A from A to A, tensor B from B to B. Now D, composition. Well, composition, for composition we need to use braiding again and associativity. So associator. So A from A prime to A double prime, tensor B from B prime to B double prime. Again, tensor A from A to A prime, tensor B from B to B prime. We're using combination of braidings and associators. We'll get to A prime, A double prime, tensor A prime, tensor B from B prime to B double prime, tensor B from B to B prime. And then here will be composition in A, tensor composition in category B. And we will land in A from A to A double prime, tensor B from B to B double prime. That was required. Okay. 3 is a trivial enriched category. As you remember, in case of sets, category consisting of a single object, 0, and identity on it, it was a trivial ordinary category. Now, what I would do, I will take letter I and make it curly. This is a magic. This will be a category that consists of a single object. Doesn't matter how to call it. I don't call it anyway at all. And object of morphisms will be our identity, or excuse me, our unit object of category V. So this is a trivial enriched category. In other words, in I, morphism from, let's call it star, not just dot star, as it will be from star to star, is defined to be I, unit object. And now theorem. So V cat tensor product and trivial category is a symmetric monoidal category. It will be closed when we will define the closed structure. So the adjoint to tensor product operation will be a little later. Where V cat is a category of small, it as ob A is a set of small V category. Also a remark, as I have used the opposite stuff, I will say that opposite of tensor product of categories is isomorphic to tensor product of opposite categories. We are just switching orders in every single component, but not between the components. And of course, that trivial category opposite to trivial category is a trivial category. And what else is that trivial category tensor A isomorphic to A tensor trivial category isomorphic to A. Okay, that's it. So now we are moving forward. We have 15 minutes left. So I will define, I guess, what is a enriched functor and self-enriched category. Yes, it's a funny name, self-enriched category. So category which is getting enriched in itself. So I would say that you will be self-enriched if you will be making money and giving them to yourself and feeling rich after this. Well, a little childish game, but in categories it works. Okay, let me give a definition. So let A, B, B, V categories. A, V functor F from A to B consists of the following data. A map of classes F from objects of A to objects of B. Let me call not F, but objects of F. And second B, for every pair X, Y belonging to A, we have a map in category V. So from A, X to Y to B, F of X, F of Y is a morphism in V. This morphism will be called F sub XY, such that the following two diagrams commute. So we will have here A from Y to Z tensor A from X to Y. If you remember, I did it on a lecture number 1 when I was describing how to write element-free definition of a function. So on one side, I'm making a composition of two arrows, F and G, and I'm getting inside object of morphisms from X to Z. From other side, I can use, I can apply my functor F to both morphisms, F and G. So I will get in B, here will be Fy, Fz, tensor B, Fx, Fy, and then compose them in category B, of course, and get to B. Here is Fx, Fz. All these things should be the same. If you would like, I would, for everyone, write here that it's f of x, f of y, f of z. It's a composition in category A. Here is a different composition in category B. Here is functor f xz. Here y z. Here xy. Okay, and the last thing is preserving the identity. So identities we preserve using the identity morphisms. So identity of x picks up element, not picks up element, it's an identity element of, you see, the names are so difficult that I'm getting puzzled when pronouncing them all. So identity element of object x is an arrow from I to object of morphisms from x to x, and identity of object fx is an arrow in the object of morphism from fx to fx. And here is f sub x comma x. So this triangle also should commute, and we get V functor. Remark. G from A op to B is called contravariant V functor. As I said on lecture number 1, the rectangle on the left will become a pentagon. You can check it yourself. The braiding will appear just because of the multiplication in category A op. It was a first remark, and second, if V equals set, then V functor, it is the same just as functor. If V is ab, then what is ab functor? Ab functor, it's additive functor. So f of f plus g equals f of f plus f of g, as you have used to. Okay, as I promised, now we will go in a very special type of category, which is called self-enriched category. when V tensor I brackets is a closed symmetric monoidal category, I want to emphasize, so I'm writing it in complete sentence, on closed category. Then V can be made in an enriched category itself. How we will do that? We will take V underline having objects the same as in V. Then second part, morphisms. So V underline from X to Y is defined to be an internal form from X to Y. And we need two more things that will fill in on the other side. So since I tensor X is isomorphic to I X comma X internal home, on this side we pick up lambda sub X, left uniter, and this left uniter goes to identity sub X. Okay, we don't know what, we don't need word sense. So here is how to define identity element of an object X. It's an adjoint of left uniter. Okay, and composition. Well, from the adjunction blank tensor A adjoint to A comma blank follows that for every X follows that for every X we have a morphism from A X tensor A to X. This is evaluation at X. It's a co-unit, of course, for this adjunction. And this is a natural transformation. This whole thing is a natural transformation. Then let's take from Y to Z internal home tensor from X to Y tensor X. Then we will go to Y Z internal home tensor Y, and then we will go to Z. So first we're using identity tensor evaluation at Y and then evaluation Z. So this map, I don't know how to call it. Let's call this map Xi. So, and again, under the adjunction, which adjunction? YZ tensor X, comma, Y tensor X, comma, Z is isomorphic to V from Y to Z tensor from X to Y, comma, from X, internal home from X to Z. So this map Xi goes to composition in V underline. So it's how to make a composition in V underline using evaluations and taking the adjoint. So I will fill the space. We will say that V underline is self-enriched category. So every closed symmetric monoidal category can be promoted to a self-enriched category using internal home as an object of morphisms. Well, we are done precisely in time, even 1 minute later, sorry. Well, thank you very much for your attention. If you have any questions, you are welcome to ask them right now or later. As usual, I did only half of the things that I prepared for today. Next time, we will go in what is to be a representable V-functor. So, what is unidal lemma? And we will define ends and maybe coends too in case of V categories. Why we get to all this stuff? In order to enhance our coend calculus that we started last time and say that it's not bound only to sets, but it's completely free to be generalized to any enriched setting. And everybody picks up their own favorite enriched setting, as I always say. You don't need to think about all the settings at once. Just pick up your favorite and be sure everything I said works there how you expect it to work. So thank you again. Are there any questions?
Are we meeting next week?
Well, I can meet next week, but next week is a spring break. So if the audience desire, we can meet since we are all graduate students and we have a professor between us. It's up to the desire of audience. We can meet also next week. If somebody don't want, you don't need to participate, or we can go on a regular schedule over the next week. So I think I will send an email to everyone with a proposition, and who will want or do not want, please respond to me. In order to make more material, to bring more material in course, I think the next week will be good to also add as today I decided to take a very slow pace with enriched categories. Even this, I know that's shocking for everyone, as it was shocking, especially for me. I remember myself when I saw all this. Why do I need to write a functor definition in such a fancy way? Yes. So slow pace in this topic helps.
Personally, I'll be traveling at this time next week, so I will not be able to attend anything on Friday.
Well, okay, then. Maybe it's really, let's take next week a break. Okay, I will think about that, and if there will be such a chance, I will of course write everyone email. But no worries about anything. I don't know how to post these notes. Maybe I will take the screenshots, make them as PDF together as a PDF, and also they will be as like bunch of notes. And of course, the recording will be available. Yes, online. I will upload this and previous recording to YouTube channel too. Well, again, thank you so much for attention, everyone. I'm stopping the recording and see you next time.
Thank you.
Thank you. Thank you.
Thanks.
Thank you.
Thanks.
Bye, Alex. Take care.
Take care too. Bye.